So, welcome everyone to my talk. So, first of all, my name is Kiszka, working for Siemens Corp Technology. I'm also a part of the Xenomai project for quite a while, even longer than I'm working for Siemens. So this is a collaborative effort, these slides as well. And all the mistakes and faults on this are mine. The rest you can keep, and the good things are definitely part of the community work. Just to clarify this. So, the agenda of the talk, I will give a little bit project introduction and background. What is it about? What are we heading for? I will talk about the co-kernel technology, how it worked, how it's now working in Xenomai. I will specifically talk about the new feature in Xenomai 3, the native support for native Linux. And then again, jump back to the topic of co-kernel, the goods and the bads in it, and how we can improve on it, how we plan to improve on it, and summarize the talk. So, what is this Xenomai? How many of you have heard about it before? Yeah, we have a marketing issue, definitely. And even the people who know it, or at least know the name, they start to think about what is this? Yeah, this is something like this old-style real-time Linux stuff. The real-time Linux extension, which happened in the early times, in early 2000s. This is something like this RTI, fork of RTI maybe even. And this is where the real-time applications are still part of the Linux kernel. And there are even more rumors like this about Xenomai. That's not really the point about Xenomai. Well, first of all, Xenomai is a RTOS, classic RTOS to Linux portability framework. That's what it's done for. That's what the project scope is. And also important these days, it comes in two flavors. The one is this classic co-kernel thing, the old style, so to say. And one is targeting standard Linux, which includes, of course, PREEMPT-RT. So Xenomai is definitely more. And just look a little bit back in the history. This is a pretty old project. It started in 2001 as this portability framework for RTOSes. So how to get your applications from all these various, sometimes dying, sometimes not really future-proof real-time operating systems on the Linux world. And as these RTOSes are usually about real-time, hard real-time, of course, this framework requires some real-time foundation underneath, even back then. And so it was looking around this project for some host, some real-time host in Linux. And, well, as these days, there were RT-Linux, there were RTI, and there were some need to improve on these layers, and specifically on the lowest part, which Xenomai contributed at this point to RTI, the ADIOS layer. Talk about the details later on. So at this point, the Xenomai core also got merged into the RTI project, known as RTI Fusion. For a while, it looked like it being the future of RTI. But then again, basically, it became clear that these two projects really got together along. So Xenomai departed again from RTI in 2005, simply because of different incompatible design goals. This lower layer evolved further to iPipe layer, iPipe patch to the Linux system. And of course, also what encroached over the time is the architecture support. So up to the point where we had up to 6 architectures running. And then, after just a short development phase, the Xenomai 3 release was announced last year. Actually, it was announced as being the next thing, the next big thing. I saw slides of myself from 2007 where I was talking about this, and so it took a while, first of all, to evolve the ideas and then also to develop them. We will see later on what was basically breaking it or slowing it down a little bit. So this Xenomai 3 now comes with a reworked core for the co-kernel approach, and it comes with support for the native Linux side. That's a brief overview of the people, the core people behind the project. So there's a maintainer, Philippe Jérôme, project founder, and, well, massive contributor, of course, to the project. There's also another guy, Jill. I don't pronounce his last name, sorry. Doing a lot of the architectural support on ARM and x86 as well. Worked a lot on the core, still working on it, of course. And also acquired a product of mine, an old project. Well, I also acquired it back then, RTNet, real-time networking stack, which is now part of the Xenomai core. And there are other guys, and there's Jose sitting in the audience as well. And myself, working on Xenomai also for, since 2003, around 2004, more or less, RTI Fusion, then Xenomai later on. So that's for the people. Who's using this actually? Well, I don't have good pictures here of all the stuff, but there is a lot of things. I'm just listing some common cases, machine control. There's a lot of machine control going on this, even PLCs. There are printing machines. One of the reference examples from Emma and Roland actually using it in large printing machines. There are printer copying machines. There are network switches. This company is actually now part of Siemens, and they're using it also for quite a while. There's another example from our domain, healthcare domain, magnetic resonance tomographs of Siemens. They have a core system sitting inside running Xenomai for real-time part and some other stuff on normal Linux. There are open source projects like Oracos for the robotics scene. In general, the robotics team and the research team is pretty strong in using this. And then there is the black part of it. I would say the iceberg part underneath the surface. A lot of applications are not publicly known or only known to a few people. This is a common pattern in this domain that people do not talk about it, what they are doing, they're just using it. So we know about some more use cases, but, well, it's not known to the public community. So it's a pretty popular project. So let's look a little bit about the technology behind it, so specifically about the co-kernel technology using it. What is it? So normally, if you look at a Linux system, well, you have the kernel, you have a scheduler, and the scheduler schedules tasks on it. Well, that's fine for some purposes. When it comes to real time, we need to do something more. There's PREEMPT-RT going on to improve the situation for hard real time. Before that, and even nowadays, there's also the approach to do it with a co-kernel, with a second scheduler, basically, scheduling a separate set of tasks besides the Linux scheduler. And that's normally for the purpose that the second scheduler can preempt the first one. So the second one is for the real-time part, and the first one can just work as it used to work without being modified. Of course, then you have events coming in. Some of these events are related to the non-critical part, and some of them are related to the time-critical part. So this interrupt has to go to the right scheduler, to the right subsystem, to be handled. And, well, in the old days, as I said, these real-time parts, the real-time tasks, they were part of the kernel even. That's how the project started back then, before 2000. But, well, these days, and even actually for quite a while now, people expect that these tasks can actually be user-space tasks, and that they can even be intermingled in the same process. So that you have the development model more or less of a normal Linux application, where part of your tasks are real-time, time-sensitive, and the other rest is doing the maintenance work, is doing, well, uncritical tasks, and all this in the same thing. So obviously, if you run these two kernels or these two schedulers in the one kernel talking to the same hardware, well, you need some kind of dispatching and collaborative management layer underneath. And this is also part of this co-kernel approaches that you have to dispatch something underneath and coordinate how the hardware is being used at the same time. And specifically for interrupts, there is this introduction of the ADIOS layer, which is basically about directing interrupts to certain domains. Domains in the sense of different scheduling entities. So you have a priority in this chain. You deliver the interrupt, but also a trap, so any kind of other hardware events triggered synchronously from, well, the source through a chain of receiving sites, domains, and each domain can decide to take the event, consume it, or forward it, or even don't subscribe to it. That's the original model behind it. Originally, there could be multiple domains. The chain could be longer, but at least one element in this chain has to be Linux, of course, the root element. And then there would be usually a higher domain and lower domain conceptually. But in the end, it turned out, of course, for our use cases, what we want actually are only 2 domains. So that's basically where this iPipe comes from, further development of the Adeos core towards this simplified model where you only have 2 domains running. So the Xenomai 2 co-kernel architecture looks basically like this, or looked basically like this. You had a nucleus, a Xenomai scheduler, and core for synchronization objects, which was a foundation, but not directly used by any of the APIs we want to build on top. The APIs in these days called skins, they were added as another component on top of this core using the services. And there were different skins, for example, to emulate or to provide a complete POSIX interface, complete in the sense for the real-time, so for scheduling tasks, for synchronization tasks. There were also skins for other RTOSes, just to name a famous one, VxWorks. There was a native skin. Native API is, well, a simplified API similar to RTI to a certain degree, more regular. So just to do that directly, setup and management of tasks, this was a variant. And then we have a driver layer. We'll talk about more details later on, which is also kind of skin on the one side. On the other side is also a hosting environment for the drivers, of course. And then you had, in addition, for each of these skins, you had a library stub in user space. So you see there's already quite complexity in this. You had to have this kernel side, you had to have the user space side, and all this formed the architecture of the classic Xenomai 2. Now with Xenomai 3, we have a little bit different thing. We now have only a so-called Cobalt core for the co-kernel part in the kernel, which is directly targeting the POSIX API. So it provides interfaces to user space in order to use or to implement a POSIX API. So user space only has a thin layer, the libcobalt, which is then providing the required services to an application in the POSIX form and talking to the core via syscalls in the kernel. And then there are, of course, also in the kernel the drivers, the RTDM drivers. And all the skins, all the former skins, all the APIs you want to implement, you want to emulate in user space for porting over from your classic RTOS, those are additional libraries on top of this libcobalt and this libcopperplate. Copperplate is another abstraction layer or another service layer in order to ease the implementation of additional APIs on top. So you have some abstraction of core objects you need in order to implement RTOS APIs. And that's basically the stacking, and then comes the application on the side. So you see that a lot of stuff has been moved out of the kernel. It's been simplified, addition of further libraries or further API implementation this way. And that's a major change in the Xenomai 3 architecture. So how do you use this from an application point of view? So specifically, if you're looking at the POSIX interface, you may realize that there's a conflict. We are implementing now in the Xenomai core another instance of POSIX aside what the system already has, the libc implementation. So you have a conflict on the symbol level, and you have to resolve it somehow so that the real-time application can pick the right one. And sometimes they may even use both. So there's a real conflict. Solution in our case is to do symbol wrapping. Maybe you are familiar with this technology. So you run the linker basically and tell then every symbol of this kind, please create in the target object not the symbol as a reference, but a wrap, then a symbol name. So let's take an example. pthread mutex logs becomes __ rep pthread mutex log. And then, of course, well, you don't have a conflict anymore. The application can then call for the real-time part. It can call for the original part if it wants to. And we provide basically with the libcobalt this wrapped implementation. So applications which are not wrapped, they use the standard libc environment. And those applications which are built according to the build process of Xenomai, they use, well, the Xenomai implementation for this. And still can use, as I said, the normal ones if they want to. And then there are some additional services specific to Xenomai, non-portable extensions, so to say. For example, change some task properties which only exist in Xenomai implementation but not in a normal libc implementation. Yeah, well, we already have quite some support for architectures. As said before, there were 6 originally. Some of them are not really relevant anymore. Others are not really ported over. So right now we have 4. ARM, of course. We have Blackfin. We have PowerPC. And we have x86. ARM, PowerPC, and x86 are also 64-bit. And x86 even have the compat layer now, so you can run 32-bit applications on 64-bit core, and you can also use x32 if you like to. I guess this is not yet really frequently happening. So as we now have 2 schedulers running, and the tasks can, well, the real-time task can choose to use normally the real-time part for the operational part, but they may have a need also to do normal Linux services. So you need to resolve somehow the case that the task want to do a normal Linux service call. For example, during setup, it's a typical phase. When you start up a task and do some preparational jobs, you want to open a file, do some communication, whatever. And then later on in the critical phase, you don't want to use this service anymore. So it should be convenient to issue normal Linux system calls. And then again, for whatever reason, a real-time task could, well, cause a fault or a trap. And this has to be handled. And we don't want to re-implement everything in the real-time part. And usually those things are not real-time relevant. So they have to be handled by Linux. And, well, also asynchronous signals could come in to the process as a whole, to a task in specific, and to a real-time task. So how to handle them? Block them, let them through. Well, in the end, what we need basically is that a task can migrate between both worlds. It should be able to run on the Linux scheduler, and it should be able to run on the real-time scheduler. Not at the same time, but, well, mutually. So basically that means if you create a real-time task in your application, you create this over a normal Linux task. So you basically end up with a real-time task having a Linux mate, so to say. And these 2 tasks, these 2 threads, they share a lot of states. Only one of them can only run at the same time, otherwise you get a mess. You have the same state, but 2 of them running at the same time. So we need a migration between both worlds. An atomic switch from real-time means suspending of to real-time means that you suspend the Linux part and you resume the real-time part. This is an atomic operation that the Cobalt core has to enable. And the same way the other way around. So if something comes in which requires handling over Linux, the Linux context, you have to suspend the real-time task and you have to resume the Linux part so that Linux can handle whatever is required for this task in normal Linux space. That's the model behind this. So tasks alone are not enough. You also need drivers usually to run the hardware. In the classic RTOS world, you often have, well, the drivers intermingled with the application somehow. Sometimes you also have in the new world for various reasons. But in most cases, when you want to share hardware, the driver is a central component which has to be sit in the kernel, and the application is separate from it. So in order to provide this environment, we need, well, a driver model. We can't use Linux directly because Linux can't handle in our environment the real-time aspects, but it can't handle real-time interrupts. It can't do real-time synchronization with a real-time scheduler. So we need a separate world for this. And in order to provide this environment for co-kernel drivers, well, we created this real-time driver model. Actually, part of my work was it in a very long time ago to provide this framework. It creates this environment in order to run drivers specifically for the real-time scheduler. So it provides basically, or the driver basically can provide an interface to a real-time application, and it expects to have a lower layer interface in order to synchronize on each other, in order to have logging mechanisms which are co-kernel ready, so have the proper semantics. The idea behind RTDM is not to reinvent the whole wheel, so everything that the driver needs in order to set it up, to interact with certain hardware environments, to reclaim resources, for example, that should be done with the help of Linux. So the normal phase of this driver consists of a startup phase where it talks to Linux. For example, a PCI driver will claim the hardware resources of the PCI bus for this device. This is all non-critical, can be done with normal Linux resources, but later on it registers an interface with the real-time core so that it gets called when the real-time task invokes this driver. There are two types of RTDM drivers or devices. This is very simple. So one is providing character device, and the other one is providing protocol devices. That's the basic model. We don't have a very complex one because we're targeting only a subset of domains here. Then there are device profiles, which aims at unifying what a driver has to provide in order to implement a UART interface, for example, or to provide other things. So we have environment for also implementing user-space drivers, so similar to UIO, this UDD, user-space device drivers, is basically the same thing for the co-kernel part. Also, RTNet is part of this, and there's a CAN implementation as well, and for IPC as well. Now look at the tooling infrastructure you have now. So first of all, you want to debug your real-time application. Well, GDB just works. That's one of the things that we enabled by letting, for example, signals through to the application. GDB is based on this mechanism. So if you receive a stop signal, for example, in your real-time thread, it will fall, of course, out of real-time. But then Linux can handle it as a normal task, and you can do the stop operation, the inspection of the task under GDB. There's some work in progress to improve basically the synchronous and the synchronization of tasks, real-time tasks, when they receive a stop signal, that all of them are stopped in the same time. Currently, there is a little bit room for optimization that some real-time tasks will continue to run, so you may not have an accurate picture of your system when a specific breakpoint is hit, for example, but this is going to be improved soon. Then there's, of course, the need for tracing in a real-time system, because usually you don't want to debug this way, or you can't debug because the interesting things only happen when things are running and not when they are stopped. So what we did as well is to enable ftrace for this environment. You may know that the Linux kernel can trace events also in NMI context, which is already kind of a co-kernel environment from Linux point of view. So the right guy just entered. Take a seat soon.
My ears are buzzing.
Yeah. So there was not much to do to enable ftrace over the co-kernel environment of Xenomai. Basically, it's about enabling or adding the right trace points so you can get the right semantic, what is going on in the Xenomai scheduler, also in your ftrace. And when it's a task, it's being migrated basically between both worlds. This is the interesting part, which is instrumented as well. So we are usually using trace command just to grab the stuff from the system and then analyze what's going on in both worlds at the same time. Why is this task now migrated to non-real time and things like this? There's also a latency tracer, which is pretty similar also to the function level tracer of the kernel. It's also pretty old technology right now, and this is something that we use just like the kernel did and does still for low-level latency issues. So if your hardware really goes crazy, you can identify basically, okay, it wasn't a software problem. There's some magic hole in your trace, which is apparently due to some hardware effects. Or you can really analyze, okay, there's a bug in the system, the low-level system, and we have really a latency issue there because of whatever. but these days no longer a big issue. We used to use it very heavily to optimize the code path, the critical code path specifically.
What exactly tool is that?
Basically it's a re-implementation of the function level tracer. So it uses the same mechanism, but it does a different visualization and different data collection because of this co-kernel, this co-kernel architecture. So you basically.
Are you familiar with the hardware lag detector in the real-time patch?
Yes, I'm aware. Sure.
Okay, would that be similar, or do you have to run your system and see it?
Well, you can use, of course, the hardware latency detector to find out if it's a hardware-related problem. But if you really have a whole system running, an application running, and you want to find out if the issue is in this particular part, not related to hardware, but a software issue, this is the tool of choice. And if there's a bug, low-level bug as well, you use this thing. Basically, I think the semantic or the feature we have there could be transferred also to ftrace. We have to add further information for the co-kernel approach to have ftrace basically aware of which context it's currently running in, if it's running in Linux context or in Xenomai context, and then you would have the same information. But right now the approach is more lightweight, so the impact on the latency is a little bit lower. It's still high, depending on the platform. And another thing that we have is quite useful for real time is a ring buffer basically being used all the time. You can do the flight recording in a more easier way this way with the ftracer as well.
Wait, the stuff from way back when? Never mind, I'll ask you later.
Okay. One of the topics often come up in this context when people debug their application is, can I run Valgrind Helgrind on my application and debug it? So for co-kernel application, you have to be aware that this is not really working. First of all, because Valgrind and Helgrind are not aware of what this Xenomai thing is about. So it comes with a set of new service calls, new system calls actually, and this is not really compatible. We could do this in theory, but no one did, and if it's really valuable is another question. These days, the approach to debug application is, we will talk about later on, is to move the application over to the native world of the Mercury. See later on. So basically run it without a co-kernel and do the debugging there. But in the end, what we often see in the field when people ask for their real-time application to be analyzed with Valgrind or Helgrind, they have a bigger problem. And that's actually the impact of these tools on the application. So the interesting things will really happen because the application stops much earlier because of timing issues. The impact of these tools are pretty heavy and for real-time application often lethal. But you have to be aware of this. So another interesting debugging tool, this is now really Xenomai specific, that comes with this hard split between real-time and non-real-time. You have to design your application around it because you have to design calling different services, so to say implicitly via the wrapping approach or explicitly that you want the real-time part to call for the real-time services and the non-real-time part to call for Linux. And that means if your real-time application, which is supposed to only service or only call the real-time services, suddenly does something else, you get a notice. Naturally, because then the task is being migrated. And that is something that we actually exploit by then sending a signal to the task, hey, you just migrate. Do you know this? And this signal, of course, can be managed, for example, by a signal handler. So the signal, SIG-debug, it's mapped on SIG-X CPU. You can register basically a signal handler on this. You can enable this. Usually you do this, of course, after the setup phase because you get a lot of signals otherwise when you're still acquiring memory or calling into files. But then if your task is in the real-time part and it does something strange, maybe call a Linux system call which is not supposed to call once in a million times, then you get the signal. And the signal, you can trap it with a GDB or you can just dump a backtrace and you know, okay, something is wrong in my architecture. And specifically interesting, if you're porting an existing application over to the real-time world, which is supposed to be real-time, but not really designed for real-time so far, that helps a lot with debugging also the application. So there are several reasons that you get, whatever reason for migration. It's basically everything that we don't handle in Xenomai, like, asynchronous signals, as I said before, syscalls to Linux, faults, so page faults. Maybe you are mapping something lazily, some mmap on a file, and then you access it. Whoops, if the memory is not available, you get a fault, and then you know, okay, something is wrong in my design of the application. And you also get a signal when some thread is about to wait on another thread, which is no longer real-time because it's migrated. priority inversion scenario. If you start to wait with a real-time thread on the whole Linux system, more or less, you're doomed. And last but not least, there's the case, well, as we know right now, no application and no task can dominate a CPU still completely. Same with Xenomai. If a real-time task is about to starve the system, eventually we can raise a watchdog signal as well, and well, stop the application at this point. So every thread should once in a while release the CPU resource and let something else be done. Specifically, Linux requires from time to time a little bit air to breathe. And that's also something you can debug this way. So if some thread goes south, that's basically what you get, a signal, okay, now let's stop and see what happened before last, maybe 4 seconds or so. We also have instrumentation by wrapping basically the calls of malloc and free. Why is this critical? If you know the internals of glibc implementation of malloc and free, there's a pool of memory available where this implementation pick normal the memory from if you do a malloc, and that's fast. That's also usually not really triggering anywhere. But when this pool is empty, it does a long path. And there are some, well, unpleasant events that you get these calls, the slow pass calls, only eventually, and after the long time. So it's really hard to debug them. And therefore, we instrumented basically the malloc free. We wrap them, and they trigger immediately when the first call happens. So if your application, your real-time application, is doing against the design a malloc in the critical path, you get immediately the call, and you know, okay, something has to be done with my application. I have to redesign something. So this tool has proven to be very useful in practice with new application, but also with the old one, as I said, just to get the architecture right. Even if the paper says everything is real-time and I've done it properly, reality often says something else, and that's what this tool is for. So I talked a lot about co-kernel side now, but as I said, there's now also Xenomai 3 for the native Linux. And so let's have a look at this. So there's now the idea behind it that we don't change the kernel anymore for this. Well, this is native. And instead, we use basically the POSIX environment of glibc, or whatever glibc you have, and place a layer on top that now enables on this environment the implementation of, well, RTOS skins. That's as simple as it looks, and it works quite well. So there are some applications, for example, of the VxWorks skin being already used, but also as well. But still, there's some part, if you want to do it really smoothly, you want to also have the drivers available that you have to implement maybe on the co-kernel side, on the non-real-time, and on the native side. So there's also the need for a driver layer, which enables the portability of the drivers over in this scenario. Because the whole vision and the goal behind it is to run, well, is to use the native interface and to enable the migration between both variants. So if you have an application stack consisting of the application and maybe some drivers, you should be able to switch the technology as you have in need. So you start maybe with a co-kernel and you identify, okay, it works well with PREEMPT-RT, maybe even sometime with upstream kernel, just switch over. Don't change my application anymore. That's the vision behind it. So currently, there are the 3 real-time APIs available in this environment. So it's VxWorks, it's a Pesos implementation, and there's this Alchemy, which is the former native skin. So this can already be used in this native environment. What's missing yet is this native RTDM layer. There is an implementation done a very long time ago by Wolfgang Gondecker, but this needs an update. Someone recently hacked a little bit on this, but I didn't see any patches on it, unfortunately. So we still need to do some work here. Once we have this, we can immediately reuse the existing infrastructures, because the assets, the bigger assets of the RTDM drivers we have, like RTNet and also the analogy stack that Jose is working on. These would be immediately available for native Linux as well. So you may wonder now, why do we need still a co-kernel approach? And that's, well, due to 2 major aspects of this. So first of all, this layer called Mercury, this native layer, they still have some functional limitations. So you can't emulate all the scheduling behavior of your beloved old real-time operating system over a Linux scheduler. There are limitations. So these systems, these legacy systems, used to be very creative in how things operate, and the application used to be very creative in requiring exactly this behavior, the exact timing behavior. And that sometimes didn't work out very well. So if you run into a situation, the scheduler that we have with the co-kernel is still more capable of emulating those stuff because it's more free, like the Linux, in contrast to the Linux scheduler. Also important that, well, some parts you trigger with a native path. In the end, in the kernel, they're not really designed for real time. If this is relevant for you in your application, depends on the application, of course. But if your application triggers this non-real-time part in the kernel, in the Linux kernel and on the libraries above, that is not really designed for real time, then you are trapped if this is really depending on you. So we can provide with a co-kernel approach also for this path solution, not all, but more. And this could also be an aspect of this. And then, again, as I mentioned before, there is this detection of non-real-time behavior of your application, which the co-kernel approach provides naturally, and that's not available with the Mercury approach so far. I think this is a general feature would be valuable for PREEMPT-RT eventually as well for developing application, but there is some work to do because it doesn't come inherently with the architecture. You have to really instrument the service and declare services real-time and non-real-time that across the whole path. But there's also a performance impact on this, and this varies a lot about the architecture you're targeting, about the performance of your target system. So usually if you go for the lower-end devices with very few cache and very few other resources, CPU power not that powerful, you see still a benefit of the co-kernel approach over PREEMPT-RT. And that varies, so I have no numbers here explicitly because it varies depending on the hardware you choose and you do also the version you choose. So sometimes it's just fixable in PREEMPT-RT, sometimes it's inherent, not that easily fixable. The co-kernel is not lightweight per definition. It also has some lengthy paths, but in general they are shorter than the paths you can trigger in the mainline kernel. And last but not least, also an aspect, something to be worked on. It's already worked on, but still there's this case that PREEMPT-RT can trigger unwanted or can have unwanted impact on non-real-time workload, which is co-located with the real-time workload. So if your system is just about real-time and everything else doesn't matter, you are fine. But for example, our MRTs, they have a small part of real-time workload and a large part of non-real-time high-performance workload. And they can be affected by the changes you have to apply on the whole system with PREEMPT-RT, which are not really, beneficial for the non-real-time part, just to have real-time on the other system part. And that's with the co-kernel is naturally, you can split it easier up. So if you really need a co-kernel, you need to find with a native approach, really depends on your application. That's the whole point about it. But the case that we maintain a lot of these things for quite a while now, and we are still maintaining it, there is a reason and there is a need behind it. So the co-kernel, has its advantages, as I said, but of course has some price as well. And that's, now I'm looking for the dark side of it. That's the patch maintenance. So this is something which is not that different from PREEMPT-RT in the sense that we aren't upstream. And a lot of things has to be done. And it's all about, is this version of my kernel supported? And is this vendor patch supported? So if you look at the current release of Xenomai 3.0.2, just released a few days ago, there is a certain distinct number of kernel patches being available, officially at least, for 3.10, for 3.14, for 3.18, for 4.1, but nothing newer. So you see also, if you look at all these numbers of the stable kernels, and if you maybe remember one or two, those aren't the latest stable versions. Also a problem. It's a measure effort, of course, to get all these things maintained. So once in a while, if there is no urgent need, those updates do not happen. And sometimes you can do the update yourself. You can just merge in the latest stable patch queue, and they are orthogonal, so you don't have any impact. But still, this is then not really broadly tested, and you may be unlucky. And actually, some stable fix actually brings in some incompatibility. And then, of course, there are all these nice vendor trees out there, specifically in the embedded world. And that actually causes a lot of trouble as well. This is the same thing with the PREEMPT-RT. You have to merge multiple patch sets, and often they are colliding in more or less subtle or obvious ways, and it's just a maintenance burden. And then with the patches that we have here, we are touching a couple of critical subsystems. Well, not as many as with PREEMPT-RT, but still, there are IRQ subsystems to be changed, there are syscall paths to be changed, the memory management system to a certain degree, but often we hit, or not often, but once in a while we hit some sweet spots there. So this has to be tested well and sometimes also debugged. So we have some regression in the past on these areas, and this is, well, just a continuous effort to work on it. So another thing that's also not very convenient is that we may have some side effects of kernel subsystems, which are usually disabled in embedded systems, but not always. And if you enable them and they haven't been tested before, you get surprises. So we had the problem, because we are running on big machines, with Xenomai, we had the problem recently with the transparent huge pages, which had some subtle issues with Xenomai, which were there covered. Actually, it was an upstream bug, but in the end, we were first of all the one to see it in reality. And yeah, this is the effect you get also if you don't have the system upstream. Maintaining all these patches required a lot of time, and the core developers, well, resources are limited. You see the list of contributors is finite, like in many projects. And these topics are typical critical parts, so the core developers often spend a lot of time on these efforts rather than working on the core aspects. And that also explains to a certain degree why the development of version 3 took that much time, simply because the maintenance of the existing system required a lot of time in the beginning. So, and there have been several attempts and also a lot of improvements in the past to make this maintenance effort of these patches easier. And there's now a new approach going on, right now mostly by Philip, but also by Jill. Again, to reduce these maintenance efforts, but also to prepare the patches that we currently have, a single patch, to be, well, more upstream-like, maybe more palatable for upstream, at least make them more fine-grained. So the main elements in this approach, the dovetail approach, is first of all to have a feature set for the IRQ pipeline, conceptually, to basically enable that interrupts are not directly delivered from the hardware to the Linux system, but can be basically directed or redirected along the path, for example, towards Xenomai. And then there are several extensions we need for the co-kernel. Well, we need this scheduler transition of tasks, as I said before. There is infrastructure required for this. We share basically CPU traps, so also there, including the system calls, we have to have some infrastructure available for this. Another feature set, the task management, like affinity, context switching, signals, and so on and so forth, the exit paths. There's also a sharing between both schedulers, which has to be enabled. There's another thing like the process memory pinning is also an important feature, which might be interesting for PREEMPT-RT as well, because there is some because there's some lazy mapping actually going on in the kernel. If you do an IO remap or a vmalloc, these mappings do not actually appear immediately in all tasks subsystems. If you're unlucky, you hit this fault path over your real-time workload. So we have in Xenomai for quite a while now some eagerly mapping of this infrastructure. And also some other things like IRQ mooting. If you're running in the real-time part, you don't want to get the non-real-time interrupts from the hardware through, because they are blocked anyway at this point. And we also, on the Xenomai part, we want to improve the usage of Linux infrastructure. In the past, this wasn't done extensively, simply because we want to be portable across different kernel versions. But these days, we focus actually in a fewer set of kernel versions. So more use of the kernel infrastructure is beneficial, actually, and no longer harmful. OK, to summarize my talk. Xenomai adds value to Linux, specifically because it enables the porting of applications from classic RTOSes over to Linux world. The co-kernel approach specifically can be beneficial in certain application domains, because it can come with lower latency than the native real-time support. So this is still a value. So Xenomai 3 was developed to renovate and expand the architecture on Xenomai. First of all, it introduced this native support for the RTOS API on native Linux. And we're also heading towards the improvement of the co-kernel patch in mainline, so that we may get the infrastructure closer to mainline. We may get it merged upstream. That's something I'm not really confident about at this point. Even if the patches are more structured and more easily integratable, we may get some parts in the mainline, but for get the whole thing over, we have to really look more on this part. This is, well, the signs are more positive than it used to be in the past, simply because the user base is growing, but still there has to be good arguments to get this thing upstream. It would help the project on the Xenomai side, of course, a lot, but still, well, it's an open question if it really works out. Okay, thank you for your attention, and I'm open for questions. And, well, also I have a glossaries collected because Xenomai has a lot of more interesting names, so if you want to look up later on, and if you want a question on this regard, there's now a list available. In the back.
To clarify, I saw a slide I came late, so I apologize, talking about the RTOS API, PSOS, VxWorks. So what that's saying is that I can write using PSOS threading call.
Yes.
VxWorks threading call.
Yeah. Yeah. Yeah.
And is that just the Mercury native API kernel, or is it also the co-kernel?
That is available for both variants.
And how robust is that? How, could I take that code and then port it and run it directly on VxWorks, or is there still some porting effort?
Well, the porting effort usually comes with the driver part of your old application, because that usually assumes that you have direct hardware access, and this is, of course, different on Linux. You have user space, you have kernel space. Most of these classic RTOSes don't have the separation, and there is where you usually have to adopt a little bit. More or less, that depends on the application design. But yeah, there are actually users who did this port this way. Took over the old application, the whole part basically, and mapped it, including on the Mercury, so on the native support of Xenomai. So Dovetail is the real re-architecture of the iPipe core. There are many details that I haven't looked up myself so far, so this is just a high-level view. There is a branch available both on the iPipe Git repository, so which is the kernel patch part, as well as on Xenomai part, in order to use this new infrastructure. It's really about breaking up the original single patch part of iPipe core into these several pieces, and doing this in a stepwise manner. So introducing the pipeline first, and introducing the hooks in order to have the task transition between both worlds. You get this feature step by step. The naming, the structuring will all be more like mainline. And this is another redesign, basically with the focus, how can we make these patches more easily integratable into mainline if they want it, at least easily maintainable as well. There will be, in the end, technically, as long as there's a patch, we have a separate single patch. But in the Git branch you see then, for a specific kernel version, you will see these patches as steps coming in, as individual commits. So you can break up the patch in multiple parts if you like to, and do individual rebasing and maybe individual picking for whatever reason. Yes? Well, conceptually, it's a kernel, so it's the same like Linux. So trust zone is something above it, so to say. There is, to my knowledge, no direct interaction in any kind of concrete projects, but maybe someone implemented something custom. We are not using it. I don't see an immediate case to use it, because then you enter a hardware-enforced different world. So the model of having the application being partly real-time and non-real-time, being a normal Linux application, this world would no longer work. And you're more in the classic, completely separated case, which you can also do with virtualization, by the way, but then it's a different programming model again. Or running multiple OSs with multiple applications on top, split. Okay, thank you for your attention.